In today's video, we'll be discussing how to program custom STM32 boards. I'll show you the differences between the old and new version of the gas sensor and how to implement code via the ST-Link and the STM32Cube IDE. To successfully be able to bootload and program your microcontroller, the first thing you need to establish is to ensure that the pinout from the datasheet and any application notes referencing the MCU you selected is identical to what you have in your schematic and layout. And the easiest way to do this is to go to the datasheet, find the exact package that you chose for your project, and go through the table of the pinout and ensure that each pin is identical to what is shown on your schematic. Now, sometimes this can be a little confusing as the datasheet will reference multiple microcontrollers and their package types, and sometimes they'll have these little notes here that say only which series of devices they're connected to. So if you're really not sure, what you could do is go to the STM32Cube IDE, pull up the microcontroller, and then select the pins that you're using. So in this case, I'm using a couple GPIO outputs, ADC, UART, and of course, the pins I need for serial wire debug. I also have pins tied to an external crystal, although for this particular microcontroller, you could actually use the internal crystal, and for the program that I'm using, I didn't need it. I'll show you how to set this up step by step in just a little bit, but this is just another way to ensure that every pin that you're using and the function that is needed is exactly what matches in the STM32Cube IDE, the datasheet, and any application notes. Also, regarding the type of bootloader that you use, make sure that everything matches up with that as well, because if you mess up the serial wire, clock, data in, out, and the reset pins, you won't be able to bootload it. So in my case, I used a serial wire debug pogo pin header. This is fairly new, as oftentimes you'll see some sort of 6-pin, 10-pin connector, but this doesn't have any pins. If you look at the footprint here, it is just a couple of pads that are surface mount, and essentially you plug in the connector and it will do all the work for you. So I'll provide a link in the description for Tag Connect, as they have a 20-pin adapter, the 6-pin cable, and you're also going to need an ST-Link V2. Unfortunately, DigiKey doesn't have it in stock right now, although I'm sure there are other websites that you could get it from. One other important note that I wanted to mention before diving into the STM32Cube IDE is that oftentimes ST will have an application note going into the exact hardware that you need in order to bootload and program your microcontroller. So in the case of my microcontroller, I'm using the AN4325 application note, and this goes into detail about the power supply requirements, the clocks, boot configuration, debug management, and any other recommendations in terms of part numbers. And sometimes even at the bottom of these application notes, they will have a reference schematic which shows you everything you need in terms of your external crystal, reset switch, boot switch, and serial wire debug connector. Now, sometimes it won't show the exact microcontroller that you're using for your project. However, just match it to the best of your abilities. And again, this is where you reference the datasheet of your MCU and verify that all of the pins match, and just connect it in a similar manner to what is shown here. If that still isn't enough for you, they also have a reference manual showing how to go through each of the different peripherals it has, whether it be GPIO, SPI, I2C, ADCs, DACs, timer channels, etc., etc. They also have a STM32 microcontroller system memory boot mode application note, which shows you the hardware connection requirements that you would need for UART, USB, I2C, SPI, CAN, and etc. So ST has a ton of different resources, even, for example, their ST-Link, the software that you need so that the ST-Link is recognized on your computer. And anything you're unsure of, just try and see if you could find an application note and then relate it to your microcontroller and make sure it's the application note that works with the series of the MCU that you selected. Here in the workspace of the STM32Cube IDE, we'll first start by going to File, New, STM32 Project. We'll then type in the STM32 microcontroller that we selected under commercial part number. Once this is done, we'll select the part number, Make sure that it matches the package that you selected in terms of the footprint, pinout, and part name, followed by next. We'll then have the STM32 project window. We'll keep the options as default and we'll type in a project name. So I'll call this STM32 F030 underscore bootload. Once the IOC loads in, you'll see your microcontroller along with several tabs where you can configure the pins. We're mainly going to be using the pinout and configuration tab and the clock configuration tab. We'll first start with the system core followed by RCC, which can be seen here. So the high-speed external clock needs to be selected as crystal/ceramic resonator. Again, I don't need this for my project. However, if you wanted to use it for yours, this is where you would select it, and it will show you which pins light up, which is PF0 and PF1. They'll turn green, which shows that they're initialized. And this is when you want to essentially go back and forth between the IDE and your schematic and verify that everything is correct. So here we have PF0 and PF1 for our crystal, so we know this is right. If we then go to system, we then need to select debug serial wire. This will then turn PA13 and PA14 green. If we go back to the schematic, we can see here PA13 and PA14 match, SWDIO, SWCLK. So again, this is why it's important for your schematic layout and the Cube IDE to all match. And the great thing about the Cube IDE is you don't need to make the PCB and then check it. You could check it before you even order your boards. So it's a great way of fully proofing your design before it's actually released. If we then go under analog followed by ADC, we now need to see in our schematic what ADC values we're measuring. So in the case of my project, I'm measuring a 3.7 volt lithium ion battery through a voltage divider and an MQ2 gas sensor. So these are tied to PA5 and PA6. So if we go back to the IDE followed by PA5, we need to select ADC IN5. And for PA6, the same thing. Now, if you notice on this microcontroller, there isn't multiple options for ADC channels. So this is when you would need to use DMA. So under this configuration setting here, followed by DMA settings, you need to add the ADC channel in order to actually use DMA. And then you need to go under the request settings and change the mode to circular. Leave everything else as default. We can now go back to the parameter settings and go under the discontinuous conversion mode and enable it. And then we also need to enable the DMA continuous requests. The end of conversion selection should also be set to end of sequence of conversion. And if we go a little bit further down under ADC regular conversion mode, we need to set the sampling time as high as possible to 239.5 cycles. Leave everything else the same as we don't need it for this project. Now, for the timer channel, this is in regards to the LEDs that I'm going to be blinking on and off. And if we go back to our schematic, we can see that we have three sets of LEDs. One to essentially show when the gas detection is low, which is this green LED here. One to show when the gas detection is high, through this yellow LED here. And another to show when the lithium-ion battery is low, through this LED here. So PA2, 4, and 7 all need to be set as GPIO outputs. So I'm going to do that first before I make this timer channel, and all you need to do for that is click on the pin and go to GPIO output. Then repeat the same for the other two pins. Once this is done, under the timer channel itself, we need to go to timer 1, put this menu down, and select internal clock. Now we'll have this configuration tab. So the prescaler is going to be set to 39,999, counter mode up, and the counter period is going to be set to 1,999. This is so that the LED blinks on and off every second. If you want the LED to blink off faster or slower, you then need to change the prescaler value and the counter period value. There's a formula for that, and I'll provide a link for that in the description. The internal clock division, we're going to set to division by 2. And everything else, we're going to keep the same except for auto reload preload. We're just going to enable that. And that should be it for the timer channel. We'll now go under connectivity, UART 1, and under mode, we're going to set it as asynchronous. Here now we will see that PA9 is lit up, but we also need to get PA10 since we need TX and RX. And again, we could verify this through the schematic. If we check here, UART TX is tied to PA9, RX PA10, which can be seen here, so we know that the connection is correct. All we need to do for this is just change the baud rate, so I'm going to change the baud rate to 115,200 bits per second. This is what I usually use for the Nucleo L476RG, and I want to keep the same baud rate to essentially keep projects consistent and have them transition from one microcontroller to another as simple as possible. Now we could go under the clock configuration tab. This part is very simple. So we have an input frequency of 8 megahertz. We're going to be using the high-speed internal for my project. We're going to select the PLL-CLK for the system clock mux, and the HCLK we're just going to set to 48 megahertz. I usually always set it to the maximum, and that's all we need to do for the clock configuration. One other thing I want to mention that I'm not doing for this demonstration, but that you should do for actual projects that you want to release. Under these pins, you could actually rename them by right-clicking and then clicking Enter User Label. So basically, whatever you put on the schematic here, try and match that to what's in the IOC. So for example, for PA2, I have it as gas low for the net label. So now we're going to go back to the IOC, right-click here, go to Enter User Label, and then we're going to type in gas underscore low, hit enter, and then there you go. So you could do this for all the pins. Again, because this is just a demonstration, I'm not going to do it here, but you get the idea. So once this is all set up for your project, you could just hit Control Save, and then it will bring up a main header file in which you can enter your code. So let's get into that. Now that we have the code generated here, we see that there's a lot of comments. So this always auto-generates whenever you make a new project and main source file. So essentially what we're going to do is just get rid of everything in green here, which we'll do that now. Alright, now that we cleaned up the code, what I'm basically going to do is take this test code that I wrote to see if I can turn an LED on and also read from the UART IC that we have connected to the microcontroller. So basically I just defined a macro here as GPIO pin 2, which if we go back to the schematic, we could see here that's the green LED, and I also just have a buffer in which I'm storing the word test to just see if it can it continuously output on the PuTTY terminal, because if not, then we're going to have some serious problems. And in the while loop, all I'm doing here is just writing the pin high and transmitting the buffer, and I set a delay of 500. So it's very, very basic code. The rest of it is just pre-generated in terms of the static voids, the initialization. This always happens when you define your pins in the IOC and initialize them, as it will auto-generate in the code for you. So again, we're just going to copy these two lines, and we're just going to copy what's in the while loop. That's really all we need for this to just get our initial program going. And before we actually bootload the microcontroller, what I want to test to see is if our project will build. So this little hammer tool right here can check that for us. Build went fine, so we have no issues there. We can now actually bootload the microcontroller, and I'm going to show you how to do that. So before we bootload the board, I just wanted to show you my debug configurations. As you can see here, make sure that it selects the project that you just created. If you have any other projects, it may set that as your pre-default, so I wanted to just let you know that to keep in mind. Under the debugger configuration, I have the interface selected as serial wire debug, debug probe as the ST link, and all of the other settings down below are pretty much left untouched. So we could close out of this now. In terms of the hardware setup, I have the gas sensor board here. We could see that the board itself has power on the green LED for the LDL regulator, and we also have some red LEDs on from the charging IC. So we know we're getting 3.3 volts at the output here, and we know we're getting 5 volts at the input of this charger. So that's a good sign. The ST-Link here has its 20-pin connector with also the 6-pin connector for the serial wire debug. Basically, all you do is put this in the board and push down when you're programming, and that's pretty much it. It's very simple. So now what I'm going to try to do with one hand here, it's going to be a little tough. I'm going to hit this debug test. And now if we look in the corner here, we can see the board is debugging. Now it's going to tell us that it wants to switch perspective, so we're going to switch. And now it's done, but so the thing that's kind of strange with this is you would think the LED would stop blinking, but it doesn't. What you want to do is go in the corner here, and you want to hit this resume button. Now what will happen is the green LED will be on. I could then terminate the program here. The green LED is still on. And this reset switch, the SWA1, if I move this to the right, press the button, turns the LED off, move it to the left, press the button, it's back on. So we know that the board successfully programmed, and now I'm going to show you in the UART terminal that everything's working, and then we could go from there. So once you bootload the board, now you could check through PuTTY to see if you could actually communicate via UART. One other thing I want to mention is if you are struggling with the debugging process, you could actually set breakpoints as you're debugging the board. The reason why the ST-Link freezes is because it stops at the HAL initialization in the int main void. So that's why you need to resume the program, and then after that, that's why the LED turned on, and we'll see in a second how the UART communication is working. So to do that, first what I want to check to see is the device even being recognized. So the way you could do that is under the search bar, you could just type in Device Manager. And then from that, you want to go to ports where it says COM and LPT. So here we have a USB serial port, COM7, and we have a chip here, FTDI. Now at first that might seem a little strange, but we do see here that it's a USB serial converter. Initially, you would think that it would be the STM32 device. However, because there's no data plus and data minus pins that tie directly to the USB connector, what's going to be recognized is the UART peripheral, not the microcontroller. So this is something I didn't know about initially, but again, it's something that is important to mention because if you are in the debugging process and you see this and you think something is wrong, that's actually not the case at all. That's a very good sign. That means that it's communicating with the IC. So again, just make sure that under ports, your device is being recognized. But once you do that, you could then search for PuTTY, go to serial for connection type, serial line, we want COM7, and we set the speed in the IOC to 115200. If we press enter here, we could see that we're getting the test value. And once again, with the switch that I put on my circuit, the boot 0 switch, if I move the switch to the right, press the reset button, it stops, move the switch to the left, press the reset button, it starts up again. And the LED also turns off as well. So here we could see that UART works. We're able to blink an LED on and off. And then from there, what we would want to do is add in our ADC code, make sure that we could read the ADC values, and then implement our gas code. Now, I was actually going to show this on video. However, I ran into a big problem, and it wasn't actually with the way that I made the code or the variables I was using or the inaccuracy of data. It's the microcontroller itself. So the microcontroller that I chose for this only has 16 kilobytes of flash, and according to the IDE in which the code I created, it won't fit on the microcontroller. So even though the code that I wrote works with the Nucleo L476RG, it doesn't fit on this board. So unfortunately, I wasn't able to fully implement everything for this. I do know that it would work because as you could see with the UART terminal, everything's fine. But unfortunately, I wasn't fully able to bring this project to light, and kind of sucks because I did really want to do that. I would essentially have to change out the microcontroller to either the 32 kilobit version or something different entirely. I didn't think it would take up that much space, but if you look at the properties window, you could actually see the size of the program itself, and I believe the program file was about 10 to 12,000 bytes, which if you do a bytes to kilobytes conversion, yeah, it does take up quite a lot. I think that's 10 kilobytes. So not including the other files that are built in the SRC, when you upload your code. So that's something that I had to learn the hard way. But one last thing I want to do now is just show you a size comparison and improvement in terms of layout and design of both boards. Okay, so here's both boards side by side. As you can see, there's a fair amount of changes. The premise of the design is essentially the same, but I think there are definitely some improvements here. The boot switch is not present in this version. The modularization of the gas sensor itself, so you could take any gas sensor module and plug it into this pin header here and then measure the gas concentration, obviously assuming you have the right size microcontroller for that. But the premise is still there. The power mux switch, which I recently made a video on, definitely check that out. Link will be in the description below. Instead of a single pole double throw switch, the FETs here were oversized, which now they are a normal SC50 package, I believe. Something like that. Very small 3-pin package. And the board itself, if we look at a assembled version before I put on all the parts for both of them, they are quite different in size. This one is slightly smaller, and there are a couple less components. Now, there were more components for the switching section, obviously, since before it was only a switch that you would do manually, whereas this one does it automatically with the power mux. But again, I think the premise is there of just making the design smaller and better. I added a custom logo as well to fit for the channel, and I'm quite happy with how it came out. It is kind of disappointing that I can't fully program it and bring it to life, but I do know that the connections are fine. I am able to read ADC values just individually without taking those ADC values and turning them into ppm concentration. So the premise is there. I think for this project, it's kind of just better to move on to something else, as I've already wrote the code for it. I made the circuit design. This is one of the first projects I've done where the STM32 could be bootloaded without just relying on a breakout board. So I think this is definitely a step in the right direction. And, I'm hoping to make more complicated projects from here. As always, thank you so much for watching. I'm trying to really grow this channel and teach you some of the processes and programming and hardware information that I struggled with. If there's anything you feel that I can improve upon, whether it be how I explain topics or just other different areas of electrical or embedded engineering that you want me to cover, please let me know in the comments below. And as always, thank you all for watching and have a great day.